Welcome. Since we were teaching line integrals and surface integrals and flux integrals recently in calculus, I thought it would be nicer to say something about fermionic and bosonic features in mathematics. So there are lots of polarizing arcs in mathematics, and Attia in an article of 2000 has once identified 6, but there are many more. For example, you can look at linear or nonlinear things, you can look at practical or theoretical, applied or abstract, exact formulas or perturbative formulas, and so on, finite, infinite. So there are lots of interesting taxonomies which you can study. And one of them is also, which you see everywhere in mathematics and also in physics, is the bosonic part. And the bosonic part is also actually sometimes hard. And then there is the fermionic part, which is anti-commutative and often easier. And maybe best example where we see that is in when we look at determinants. Determinants are easy to compute. We can compute them in polynomial time. By permanence, we don't know how. Probably needs exponential time. So permanents there's no negatives and there's no cancellation. So in the fermionic part, you usually have these cancellations, and maybe from the algebraic part, you have this exterior algebra which appears in Fock calculus. So if you take it's a multilinear algebra, you take a Hilbert space and then you look at, say, something like creation and annihilation operators, and this is the commutator bracket, and on the other side you have the anti-commutator, so that you have the anti-commutator brackets. So this is maybe more Jordan algebra, this is more Lie algebra part. But it's kind of interesting what happens also in physics. You have matter is described by, featured by fermions. You have the fundamental particles like the quarks or the leptons are fermions, and then on the fourth side you have the bosons, for example the vector bosons or the Higgs boson or the gluons or the photons or the graviton. We don't know yet, but these are forces and they are described from the bosonic part. I just wanted to kind of also put a little bit of things. I have once kind of had fun with primes, number theory. There are primes of the form, the odd primes either of the form 4k minus 1 or 4k plus 1, and I think about primes of the form 4k minus 1 like 7, for example. I think about them like these are neutrinos, these are fermions, and the ones which are 4k plus 1 like 5, they are not fermions, they are bosons because they decay, and they decay into 2. So that's in the complex, they decay. For example, 5 is 2 plus I times 2 minus I. So every prime of this form, can be written as a sum of 2 squares, and that's the Christmas theorem of Fermat. And so this has the consequence that in the complex you can actually write them fundamentally as the product of 2, fermions, which are. So that's why it's considered a boson. So that's not only kind of a game, it's actually very useful, because when you look at the quadratic reciprocity theorem, and so you look at this Legendre symbol which tells whether P is a quadratic residue or with respect to Q or not, what you can say is, so this behaves a little bit like a fermion, because when both are fermions, both primes are fermions, then the sign changes. So that's kind of what happens when you switch to fermions. And if one of them is a boson, this doesn't. It's not the case, and the sign is the same. So that's how you can remember the quadratic reciprocity theorem. I also had some fun with primes in the Quaternions. It's very interesting. So there are 2 types of primes. So there are the Hurwitz prime and there are the Lipschitz primes. So there are 2 types of primes there. And you can look at different equivalence relations over there. The units, there are 24 units in this integer space of integers, and then you have you can look at things modulo u, or you can look at the group generated by permutations of the axis, and also so there are 4 axes, 4 factorial, but then there's also the flip. So what you can look at, and what I looked at in 2016 was look at the U equivalence classes among the V equivalence classes, and it's very interesting there that you see kind of 2 types of hadrons. You see the mesons, or you see the baryons. So you have classes which consist of 3 elements, classes which consist of 2 elements, and that's it. So that's kind of a very interesting kind of course that's just maybe a manifestation of some mathematics, maybe some, doesn't mean that it's fundamental, but it's interesting, so you can kind of understand also some number theory from that perspective of fermions or bosons. Also, something I was interested in a couple of years ago was positive curvature manifolds in the context of the Hopf conjecture, which is still an open problem at even-dimensional manifolds of positive curvature are believed to have positive Euler characteristic, but that's an open question. But what you can do is you can also look at the list of positive curvature manifold. That's the complete list. We don't know any more even-dimensional positive curvature manifolds than this, and you can think this is the whole list. And I personally think this is the whole list. There are some reasons why you can believe that it's over with this kind of exceptional parts, and then you have the division algebras R, C, H, and O. And so what I did once is a kind of a little game here and associated this to bosons in the standard model. It's interesting that in both cases we don't know the complete list of bosons in physics because we don't know all the forces. Maybe they are all, I actually believe they are all, and also we don't know the list of all positive curvature manifolds. Maybe they are all. This is the complete list, maybe, of all positive curvature manifolds. And then you can speculate that odd-dimensional manifolds somehow are associated to fermions. I don't know. I mean, one of the things you see, odd-dimensional manifolds has 0 Euler characteristic. You have 0 Euler characteristic, also the 0 eigenvalues match, right, by Hodge theory. So what you have is, in general, the non-zero eigenvalues by McKean-Singer, they in the even and odd-dimensional forms, they correspond to each other. That's some sort of supersymmetry, but that's broken, say, for manifolds with the Euler characteristic not 0, because the zero eigenvalues don't match up, right? The number of 0 eigenvalues in the even part minus the number of 0 eigenvalues in the odd part, that's the Euler characteristic. It's just the dimensions of the kernels of these Hodge blocks. And so this is kind of some manifestation that there is something fermionic here. But something which is very dear to me, because we are teaching this all the time, we are teaching calculus, we are teaching multivariable calculus. So when we do for example, when we compute length, when we compute area, when we compute volume or mass, we use a Archimedes integral. We divide things up, and we don't care how we add things up. Right? So this is orientation oblivious, and so that's a bosonic integral. But then we have a fermionic integral, which is kind of needed when you are going, and so when you use the fundamental theorem of calculus, as obviously this is a fundamental theorem, for example, a to b f prime t dt, that's f of b minus f of a. So that depends on how you integrate. Differential geometry course, you realize that the f prime is actually, that's here in this Leibniz story, that's a 1 form. It's not a 0 form. So this actually is a different mathematical object. But 1 forms and 0 forms are, isomorphic, so it doesn't really matter. But still, kind of, you can take the formalism from higher dimensions, and you can actually get the exterior derivative gets you to a 1 form, and then you take the inner derivative, brings you back to a 0 form, and that's actually what we are considering. And you have actually ixd plus dix that's the kind of in general for differential forms, that's called the Lie derivative, and that's the Cartan formula. So that works for arbitrary forms. You can also take the derivative on a one form, right? So that's what you do in complex analysis. For example, you take harmonic one forms, for example, and so everything, of course, is similar. So there is this isomorphism. And then also in higher dimensions, we have this surface notion of surface integrals, which is actually just a generalization of the surface area. You weight it. It's kind of measure theory. You're taking a measure on the surface. Measure theory is completely orientation oblivious, except if you go into geometric measure theory, where you look at differential forms, measure like the Ram currents, for example. These are kind of you push things also. You can push this also into measure theory. But the real generalization here is integral geometry. This is probabilistic when you compute things using probability theory. For example, you take the arc length and you compute it using the Crofton formula. So you can do things also probabilistically. And that's typical in probability theory. That's Bosonic nature. It doesn't matter on the orientation. It's completely orientation oblivious. And also then if you look at scalar line integrals, that's just a generalization of the arc length. Arc length is something which is completely independent of the orientation. When you go from A to B or go from B to A, you get the same result. And which sometimes is a little bit confusing for students, but the line integral here, the line integral really depends on the orientation. So this is a Fermionic story. This is a Bosonic story, and often we mix these things up, and that produces confusion. And I only realized this really kind of well when I was looking at kind of calculus in the discrete. If you look at calculus in the discrete, and then you have when you have a function on vertices, that's a scalar function, and you take the gradient is then a function on the edges. For example, if this is 3 and this is 2 here, then it's 3 minus 2. So what you do is you introduce an orientation on the graph. You make it a d-graph, an oriented graph. And that's what you actually do when you want to compute things, like for example, you want to compute area using the planimeter idea, using Green's theorem, or you want to compute volume using the divergence theorem. What you do is you introduce an orientation structure. And that's what you can do also on graphs. You can make it oriented. And then when you do it, make it oriented, there are things which do not depend on the orientation, like area or things like that. And also homology you do. When you compute homology, you start with an object which doesn't have an orientation. You make it, or you just introduce randomly, how you want it. It doesn't matter. You just produce an orientation on each simplex. And then you introduce the exterior derivative, and you have the exterior derivative. You have d plus d star is the square. That's the arch Laplacian that decays into different blocks, and each block has as a kernel. The dimension of the kernel is the kth Betti number. And so if you want to compute the homology, this doesn't matter on how you have oriented things. So it doesn't have to be an orientable surface. You just produce an orientation, make it somehow fermionic, and then you do the computation here, and then in the end you get things which are independent of the orientation, like cohomology. So that's the that's what I wanted to say today.